To understand the literature on treatment effects, you'll need to develop some familiarity with the concept of conditional independence and its properties. This video provides a short overview. Before we move on to conditional independence, let's start with plain vanilla statistical independence. We say that two continuous random variables x and y are independent if and only if their joint density function is equal to the product of their respective marginal density functions for all values x and y in their respective support sets. By using the definition of a conditional density, we can show that this is exactly equivalent to saying that the conditional density of y given x is the same exact thing as the unconditional density of y, or if we flip the roles of x and y, that the conditional density of x given y is exactly the same thing as the marginal density of x. So how do we know that these three characterizations of independence are in fact identical? Well, I'll show you the calculation for the equivalence between the first and the second definition of statistical independence. By definition, the conditional density of y given x is the ratio of their joint density to the marginal density of x. Now, using this property with the blue star next to it, namely that the joint density is equal to the product of the marginals, that's our primitive definition of independence, we can simplify the expression for the conditional density as follows. Now notice that the marginal for x cancels out in the numerator and the denominator, leaving us with the unconditional density of y. We could have used very similar reasoning to show the calculation for the conditional density of x given y, and indeed, if you replace probability mass functions for probability density functions, all of these calculations will go through for discrete random variables as well. The easiest way to understand independence is by looking at the second and third characterizations on this slide. These say that y and x are independent if and only if knowing y tells you nothing about x, and knowing x tells you nothing about y. These are both equivalent. And that's exactly what these conditional densities say. Conditioning on x, the distribution of y is completely unchanged from its marginal distribution. And conditioning on y, the distribution of x is completely unchanged from its marginal distribution. Because independence is such an important concept, it's helpful to have some shorthand notation to show that two random variables are independent of one another. We use the following symbol, originated by Phil David, to express the idea that x and y are independent random variables. The intuition for conditional independence is very similar, except now the relevant statements only hold conditional on a third random variable, z. As before, we'll give three equivalent characterizations. The first one says that the joint density of x and y given z is equal to the product of the respective conditional densities, namely that of x given z multiplied by that of y given z, for all possible realizations x, y, and z of these three random variables. The second characterization says that the conditional density of y given x and z is identical to the conditional density of y given z alone. In other words, once you know z, x doesn't tell you anything extra about y. The final characterization reverses the roles of x and y. This one says that the conditional density of x given y and z is identical to the conditional density of x given z alone. In other words, once you know z, y tells you nothing else about x. As before, it's useful to have some shorthand notation. For conditional independence, we use the same symbol as we did for unconditional independence, except here we add a conditioning bar to show that we must condition on the variable z in order for the relevant independence condition to hold. Conditional independence satisfies a number of useful properties. In fact, you could define conditional independence without any reference to probability distributions just by listing a set of axioms and deriving all of the related consequences from those axioms. That might sound a little silly, but in fact, this way of looking at things can be very useful in problems where you need to take one conditional independence statement and turn it into a different conditional independence statement. The first axiom of conditional independence is symmetry. Symmetry says that if learning y tells us nothing extra about x, then learning x tells us nothing extra about y. This is probably the most intuitive property, and indeed we actually proved this a couple of slides back when we started to look at independence. There's no widely accepted name for the second axiom of conditional independence, but to avoid repeatedly saying second axiom of conditional independence, I want to give it one. I call the following axiom redundancy. It says that, conditional on y, x is independent of y. To understand the motivation for the name, recall the definition of plain vanilla independence. X and y are independent if and only if learning y tells you nothing you didn't already know about x. Viewed from this perspective, the redundancy property can be read as follows. It says that if you already know y, in other words, conditional on y, then learning y can't possibly tell you anything new about x. It seems like a fairly useless property, but in fact it can be very helpful in proving more complicated aspects of conditional independence by combining it with the symmetry property from above. Reversing the order of the random variables on each side of the independence symbol, we obtain the following. In words, this says that y is independent of any other random variable x conditional on y. The third axiom of conditional independence is called decomposition. Decomposition says that if x is independent of y given z, then x is also independent of any measurable function of y given z, where here h is used to denote some arbitrary measurable function. In words, the decomposition property says that if learning y tells you nothing additional about x, given that you already know z, then the same is true for any function h of y. A common application of decomposition is dropping random variables from a conditional independence statement. The key here is that all of these axioms hold regardless of whether x, y, and z are random variables, random vectors, or arbitrarily complicated collections of the former. So interpreting this function h as the function that takes a vector x2 and x3 and simply drops the second element, we can use decomposition to show that if x1 is independent of x2 and x3 given z, then it's also the case that x1 is independent of x2 by itself given z. The fourth axiom of conditional independence is called weak union. This axiom says that if x is independent of y given z, then x is also independent of y given z and any measurable function of y. Weak union is often used alongside decomposition as follows. Suppose that x1 is independent of x2 and x3 given z. Then, by weak union, x1 is also independent of x2 and x3 given z and x3, since x3 is a function of x2 and x3. Finally, by decomposition, we have that x1 is independent of x2 given z and x3. In effect, we've moved the x3 from the left of the conditioning bar to the right. This is a very common pattern that you'll see in arguments using conditional independence. The final axiom of conditional independence is called contraction. This one has two hypotheses. Suppose first that x is independent of y given z, and second that x is independent of w given y and z. Then, x is also independent of y and w jointly given z. In effect, contraction allows us to move a random variable from the right-hand side of the conditioning bar to the left-hand side, exactly the opposite of the pattern that we used a moment ago by combining decomposition and weak union. The axioms of conditional independence can be used to prove a number of useful facts. Here's one. Suppose x and y are independent given z. Then, applying decomposition, x is independent of h of y given z, where h is a measurable function. By symmetry, h of y is likewise independent of x given z, and applying decomposition a second time, we find that h of y is independent of g of x given z, where g is another measurable function. Finally, by one last application of symmetry, we have g of x is independent of h of y given z. So we've shown that if x and y are independent given z, then so are any two functions, g of x and h of y. A familiar property, but very easy to establish directly from the axioms without having to do any kind of hard thinking about the definition of independence, working with any integrals, or anything like that. Conditional independence has many implications, but among the most important are those that concern expectations, i.e. means. Suppose that x and y are independent given z. Then it follows that the expectation of xy given z is equal to the expectation of x given z multiplied by the expectation of y given z. Moreover, the expectation of y given x and z is simply equal to the expectation of y given z. And if we exchange the roles of y and x, we have a related expression, namely the expectation of x given y and z is equal to the expectation of z. These last two properties are often called mean independence to distinguish them from the notion of conditional independence. So we would say in this example that, in number 2, y is conditionally mean independent of x given z, and in number 3, x is conditionally mean independent of y given z. Conditional independence implies mean independence, but the reverse is not true. It's possible to have random variables that satisfy 2 and 3 without it being the case that x is independent of y given z.